Welcome to today's lesson, which is on section 1.5, continuity. So we're going to start today going over the definition of continuity, looking at some questions about continuity, whether functions are continuous or not. And then we're going to finish up this section looking at the intermediate value theorem. So again, all of these having to do with continuous functions or where functions maybe are not continuous. Okay? So in high school, somewhere when we first did algebra, we all learned that for a function to be continuous, basically that meant if you could graph the function without picking up your pencil, then it would be continuous. That was the easy way to kind of tell. And that's true when you look at a function, but in calculus, if you are asked to prove that a function is continuous, then you have to look at these three basic rules that will define whether or not a function is continuous. So if you look at this definition at the top of your notes, it says a function f is continuous at a number a if, and then all three of these things have to be true. F of a has to exist. Number one, f of a has to exist. Number two, the limit as x approaches a of f of x has to exist. And remember what that means. For the limit to exist, it has to equal the same thing coming from the left and the right of a. And number three, most importantly, that the limit as x approaches a of the function f of x has to equal the function value f of a. Okay, so when you're asked to prove or show that a function is continuous at a point A, you have to show all three of these things. If it asks you to explain why it's not continuous, then you would say it's not continuous because of one of these three things. Or maybe two of the three things aren't true. Okay, but as soon as you find one of those three things that are not true, then the function will not be continuous. All right, so down at the bottom it says a function is defined as continuous only if it is continuous at every point in the domain of the function. This is important because as we go through this section, you'll see that we know that certain functions are continuous everywhere, and so we don't have to check every single point. There's only points that we have to check are where there's going to be breaks or changes or something's going on there. Okay, so that's kind of important because I don't want you to think you have to check every single point on a function. That's not what this is about. This is at specific values in the function. Okay, so these a values. All right, so let's look at the first example. It says for each below, determine whether the function is continuous. Again, to be continuous, that means that the limit of f of x as x approaches a has to exist, and the function value has to exist, and both have to be equal. Okay, those are three things up here that has to be true. All right, so just by looking at these graphs, if we just go back to the the method, if I have to pick my pencil up or if there's a break, it's not continuous, then I can easily see that all of these functions are not going to be continuous, okay, at A. Now, so that's what I'm talking about. It's continuous. All of this is continuous. All of this side is continuous. But right here at A, that's where there's a problem. So that's the only point I have to check is where I think it is or isn't continuous. All right, so for the first one, we would have to go through these three things. So I would start with number one, and I'm not going to write Roman numerals. I'm just going to write 1, 2, 3 on my checking over here. So number one, I would have to find f of a. Okay, that's the first thing I have to do. Well, f of a is the function value at a. So there's a hole there, which means there is no function value. The function value doesn't exist if it's an open circle. So automatically, I don't even have to check 2 and 3. This is not a continuous function because the rule, step number one, failed. Okay, there is no function value. Okay. Now, just kind of going on, does the limit exist? If I were to look at number 2, okay, I could stop now, but I just want to keep going. The limit as x approaches a does exist. Okay. How do I know the limit exists? remember, if I approach the same value from the left and from the right, if those two values are the same, then the limit does exist. Okay, whatever that value is. I don't have any y values here. You know, if I were to draw, let's say 1 and 2, then the limit as x approaches a from the left would be 2, and the limit as x approaches a from the right would also be 2. Okay, so the limit does exist. Okay. But I don't really have to do that because step 3 is to show that the limit and the function value are equal. Well, the function value doesn't exist, so there's no way that can be equal. Okay, so this is not a continuous function. Okay, so we're going to say number 1 is not continuous. Okay, not continuous function because it failed number 1. All right, now some of you in high school learned that there's different kinds of discontinuity. Okay? If a function is not continuous, we say it's discontinuous at that point. So when you have a hole in a function, we call that a removable discontinuity. Okay, so maybe those names sound familiar to you, so that's what that would be considered, a removable discontinuity at A. All right, number 2. Okay. Let's go over those 3 things. So number 1, can I find f of a? Does it exist? Okay. Yes, there's a point right here at A, closed circle, so that would be the function value. Again, whatever it is, let's say it's 1. Okay. So it does exist. All right, number 2, the limit as x approaches a of f of x. Does that exist? Well, the limit from the left side of a is approaching, let's say again, 1 down here, and the limit as x approaches a from the right is not approaching 1, it's approaching 2. So the limit would not exist. Okay? So again, number 2 is not a continuous function. Not continuous, okay? Because of step number 2, the limit didn't exist. All right, this kind of discontinuity is called a jump discontinuity. When the graph actually moves and continues in a different place, that's called a jump discontinuity. Okay, so we have removable and we have jump. The third one, okay, step 1, can we find a function value? Well, at A, there is an asymptote. If there's an asymptote, there is no function value there. So the function f of a value does not exist. Number 2, does the limit of x approaches a of f of x exist? Okay. Well, remember, for the limit, if limits go to infinity, right now we say that doesn't exist. Okay, remember, we talked about that. That's going to change in section 1.6. But for now, if we don't get a number, if it goes, there's no number, then it doesn't exist. So I didn't really have to check number 2 because I already failed number 1, but just showing you kind of on both. So this is not a continuous function because of all of that. Okay. Now, this kind of discontinuity is what we call infinite, when the limits go to an infinity, positive or negative. So we have 3 different kinds of discontinuity: removable, jump, and an infinite. So all a little bit different. Okay, number 4, okay, function value for step number 1. Can we find f of a? Yes, we can, right there. Okay, there's the function value up here. So it does exist. Okay. Number 2, does the limit as x approaches a of f of x exist? Okay. Well, we got to go from the left side of a, we approach this value right here, whatever it is. And from the right side of a, we approach that same value. Okay. So the limit does exist. So this is the first one where we have both things existing. So now we get to go to step 3, and there's a problem because the function value is here, the limit is here. So those do not equal each other. So f of a does not equal the limit at x approaches a, right? They don't equal the same thing. So this one fails for that reason, okay? So step 1 was good, step 2 was good, but like I said, step 3 is the most important, that those two things have to be the same. So this is also not a continuous function, okay, because it failed number 3. And again, looking at this is, a lot of times students have trouble telling whether this is jump or removable, okay? Remember, to be a jump discontinuity, the function has to be in a different place. This function is continuous and it doesn't change except for that one point that moved. So this one would be considered removable. Okay. I have students that would say this is jump, but it's not. To jump, the rest of the whole graph has to be moving in a different place too. Okay? All right. So that's just kind of to show you the discontinuities, kind of how they look and what you're doing using the definition from above. Okay? All right, now, these directions go for the next page. It should be on the next page, but it says for each, determine whether the function is continuous. If not, where is the discontinuity? And Dr. Taylor did these with you. These are on the intro videos. Right? Those are the directions for 5, 6, and 7. They just happen to be on the wrong page. Okay, so he did all these with you, and I'm not going to go over them with you, but I mean, you have them already, hopefully written down. I do just want to talk real quickly to remind you that we know certain functions are continuous everywhere. Okay, we know that. We also know that some functions are continuous everywhere except for problem areas. So when Dr. Taylor went over this with you, a rational function is continuous everywhere except for points that make the denominator equal to 0. Okay? So the only place I really have to test is this continuous would be at 5. I don't have to test anywhere else because I know that rational functions are continuous everywhere except for where the denominator would be 0. When you have a piecewise function, okay, 6 and 7 are piecewise functions. When you have those, look at each individual function. So negative 6 minus x, that's a linear function. That's continuous everywhere. F of x equals x, that's a linear function. So it is continuous. X minus 1 squared, that's a parabola, which is continuous everywhere. So my problem isn't within all of this part. My problem is where it changes from here to here and where it changes from here to here. Okay, do the graphs connect or don't they? So you're only having to check for discontinuities at the breaking points, which is this part, right, where the domain is over here. So I would have to check at -3 and at +3. It's the only two places there would ever possibly be a discontinuity. So you need to kind of understand what it is that you're checking. Okay, that makes this process obviously a lot easier. So if that's not making sense to you, then let me know, because that's the whole part of this. And a lot of students have trouble with piecewise functions, and that's a huge part of this section. And what we do in here is look at piecewise functions. All right, and then he did number 7. So again, this is a quadratic, which is continuous everywhere. Y equals 5 is a straight horizontal line at 5. That's continuous. So I don't have to check every number. I only need to check where it changes, and that would be at 2. Okay? So I know that he did all those with you. You found out that number 5, it was not continuous at 5 because there was no function value. F of 5 didn't exist. Over here, okay, you were continuous at -3 because the function value and the limit was the same, but at +3, the function value and the limit was not the same. Okay, so you had a discontinuity on this problem only at 3. And then number 7, all you were checking was 2, and f of 2 was 5, and the limit as x approaches 2 is also 5. So this one was continuous everywhere. Okay? All right, so I know I spent a little time on this, but it's important. It seems simple enough, but there's a lot of little things in here that you got to make sure you understand. All right, moving on to number 8. Dr. Taylor did this one with you, and I'm going to do number 9 with you, but these are asking us to determine the value of c so that the function will be continuous. All right, so this is kind of moving into what we just talked about. If we have a piecewise function and I want it to be continuous, then the number where it breaks at, those have to be the same on both functions. That function value has to be the same. So if I look at the one that Dr. Taylor did, I know that a quadratic is continuous everywhere. This is a line, it's continuous everywhere. But what I'm concerned about is what's happening at 3. So at 3, if I can make both of these things equal, then I know that it will be continuous. I know that, okay? So that's what he showed you how to do. And so we're going to go through this again and do it for number 9, okay? So looking at my piecewise function, cx plus 7, that is a linear equation. It is continuous. Cx squared minus 7, that's a parabola. It's continuous everywhere. But where these two meet, that's my problem. And where are they going to meet at? In this case, they're going to meet at 8. So I want these two equations to be equal to each other when x is 8. That's what I'm getting ready to do. So I want to set cx plus 7 equal to cx squared minus 7 at only x equals 8. Okay, that's what I'm trying to help myself make this thing continuous. I'm going to pick the right c value so that all this works. So we're going to plug in 8 for x right now. So that would be 8c plus 7 equals, and then if I plug in 8 for x, 8 squared is 64 minus 7. Right? And then we're just going to solve that for c. Okay? So I'm going to go ahead and move this negative 7 to this side and make it 14. And I'm going to bring the 8c over to this side. So 64 minus 8 is 56c. And then I'm going to divide both sides by 56. So I end up with c equals 14 over 56. Okay. Now, I'm going to reduce that. 14 goes into both numbers, but it's a good point to stop right here and talk to you about WebWorks. So in WebWorks, if you put in 14 over 56, it will take it. You don't have to reduce numbers in WebWorks. So you're fine doing 14 over 56. I do not take off. If you were doing a test for me and you turned in a paper with that, I wouldn't mark off. Okay, I don't take off for not reducing. But just keep in mind, since you're taking quizzes and tests on Canvas, if they happen to be multiple choice questions, they're probably going to be reduced. So just that you know, you need to be able to find the answer, but you could put in 14 over 56 in WebWorks and it would be fine. Or you could put in 1/4 into WebWorks and it would be fine. So WebWorks will take your answers even if they're not simplified, okay? All right, so that's how you do piecewise functions. Those are very typical kinds of problems when you're asked to find values that make a function continuous. Okay. All right, let's move on to number 10. I like these two problems because it helps us remember a little bit about the domains of logarithmic functions and for trigonometric functions, which a lot of you haven't done in a while. So we're going to take a little bit of time and talk about this. So I like number 10 because it leads us into this, back into looking at a domain. In calculus, for you guys to know what the domain is of functions is hugely important. So, part of the review stuff that you were doing before section 1.3, a lot of it was about the domain. The reason why we keep harping on that is because when you get to calculus, everything revolves around the numbers that are in the domain. So if the numbers aren't in the domain, then you don't worry about them. They're not important. So if you don't know the domains, then that's going to be a problem when we get into later sections. All right, so let's look at this and I'll explain why that's important. Okay, so earlier on that rational function back on the other page, actually it was on this page, sorry about that, this one up here. Remember I told you that rational functions are, the domain is all real numbers except for what makes the denominator equal to 0. So if I look at number 10 off the top of my head and I'm thinking, oh, this is a rational function, so I just need to figure out what makes the denominator equal to 0, that's a good start, but that's not going to be my answer. The reason it's not my answer is because I don't have a polynomial up here. I have logarithm and I have a trig function. So the domains of those are different, okay? All right, so I need to look at the domains of everything and then kind of put it all together. All right, so this is a good review. When you have logarithms, remember logarithms have to be positive numbers. They can't be 0 and they can't be negative. So the domain for the natural log of x has to be greater than 0, okay? That is true for logarithms. Okay, let me put this over here. The natural log of x. Should be written like that, but all right. So whatever your variable is, or whatever you're taking the log of, that has to be greater than 0. Now, for the sine of x, okay, if you remember your trig functions, the domain for sine is all real numbers. There's not a problem with those, okay? All right, and then for the denominator, for our rational function, okay, I'm going to put denominator because that's all we care about. For the denominator, the domain, x squared minus 1 can't equal 0, right? We can't have 0 in the bottom. So I could factor that, x plus 1, x minus 1 can't equal 0. Set each of those equal to 0. So we end up with x can't equal negative 1 and x cannot equal positive 1. All right, so if that's the case, if that top piece right there wasn't there, then that would be my answer, okay? But look at your domain. We can only use numbers greater than 0. So if you're only using numbers greater than 0, this one isn't even part of the domain. That's out of our, we don't need that one. So this is the only number in the domain that's a problem. So where is this function discontinuous? That would be at x equals 1, okay? All right, so again, the domain is real important on this one. All right, number 11, this is a natural log that includes a trig function in it. All right, so remember what I said over here for logarithms, the part you're taking the log of, that has to be greater than 0. So in this problem, what are you taking the log of? You're taking the log of 1 plus the cosine of x. So that means 1 plus the cosine of x has to be greater than 0, okay? So this is the domain. All right, well, if 1 plus the cosine of x has to be greater than 0, then the cosine of x has to be greater than negative 1, right? Just solving this. And remember, this is an angle, right? X is the angle that we're talking about. So if I just go back real quick and look at the cosine value, okay, cosine starts up here, goes like this, and keeps going, back this way. So there's your cosine graph. So all cosine values are between negative 1 and 1, if you remember the look of that, and it keeps going forever and ever. Okay, so this is saying that the domain of the natural log of this cosine of x has to be greater than negative 1. Well, there are many, many places on this graph where the cosine of x is equal to negative 1. Right? That's the lowest points. So do you remember where the first one is on that? Okay, where does the cosine value equal negative 1? So let's remember that that would be when x is equal to, well, can't equal pi. Okay, that's the first value right here is pi, where you have negative 1. Okay, so if x can't equal pi, that means it also can't equal this value, and then the one over here, and so forth, and then same thing back here. So if you remember how to get to the next point, you add the period, and the period for cosine is 2 pi, one rotation around the circle. So that means if I added 2 pi to pi, I would get 3 pi. If I added 2 pi to that, I would get 5 pi, then 7 pi, right? So all of those are part of the numbers that are not continuous. Okay, that's where there's a break. So also backwards, if I subtract 2 pi, that's negative pi, negative 3 pi, and so forth. So there's two ways that you can write it, okay? Hopefully you remember in trig, when there are multiple answers, we're going to use k, right, to represent any integer. And then the way that you write what x cannot be to list all of them, you would say the first one, which was pi, and then you add the period times k. That takes care of all of them. Okay, that's one way to do it. Now, you could go old school on me and list them, and you would say dot, 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 and then you could do negative 5 pi, negative 3 pi, pi, negative pi. It's not coming out very good. Negative pi, pi, 3 pi, 5 pi, and then dot, dot, dot. Right. That's the way that you could list all of them and, listing them, because there's an infinite number of places where we have a discontinuity in this problem. Okay, so this is just a short way to do it, but this would be okay as well. All right, so you can see that, yeah, discontinuities when it's just regular functions, maybe not so bad, but so I said earlier, finding domains and understanding what you're actually given, that's a whole nother thing. And that will help you to figure out what it is that you are looking for. Okay? So these are good two problems just to kind of remind yourselves that we got a lot of functions that we're working with in calculus. Okay? Not just polynomials, not just, ones that are a little more simple. So these are two good problems right there. All right, let's look at number 12. All right, this is a new definition. We've already talked about limits quite a bit, so this is just kind of an addition to all of the things that you understand about limit. So this says a function f is continuous from the right at a number a if the limit as x approaches a from the right of f of x equals the function value, and a function f is continuous from the left at that number a if the limit as x approaches a from the left of f of x equals f of a. So all this is asking you, okay, in a nutshell, is first find the function value f of a. Then to know whether or not it's continuous from the left or the right, you look at the limits from the left and the right. And whichever one equals the function value, that's the side it's continuous on. Could be continuous on both sides. Okay, so you have to figure that out. You can kind of see it on the graph. Those of you that understand limits very well, you kind of know what side it's working on. I always say, look at the closed circle, because the closed circle is the function value, right? So whatever side is approaching the function value, that's the side that's continuous. It's continuous from, okay? So you kind of can see it on the graph if you understand that, but algebraically, you would have to show this information, okay? So let's look at x equals negative 3. What is the function value at negative 3? That's the first thing you want to find, because for both you need the function value. So f of negative 3 is right here, which is at negative 1. Okay? So then you're going to do the limit as x approaches negative 3 from the left, okay, of f of x. And then we're going to do the limit as x approaches negative 3 from the right of f of x. So let's see what we get. So if we find the limit as x approaches negative 3 from the left, that would be this way, coming in from the left, we would get negative 1. Okay? If we take the limit as x approaches -3 from the right, we would be coming this way. And that would be right here, which is about, we'll say, -1/2. Okay, so which one was equal? Okay. That was equal to the function value, so that means this is continuous from the left. That's the side that was equal. All right, same thing for B. Are we continuous from the left or the right when x equals 1? So first we would find the function value. What is the function value at 1? That would be 1. So now we would look at the limit as x approaches 1 from the left. And we would look at the limit as x approaches 1 from the right. And see which one equaled 1, or if any. So let's go from the left-hand side of 1. We're coming to 1 from the left, that would be here, which means we're approaching 2. And if we approach 1 from the right-hand side, we're approaching the number 1. So this is the one that's equal to the function value, which means this is continuous from the right. So it's kind of straightforward, but you still have to show the work, so that's what you would do. All right, let's look at number 13. Show that f of x has jump discontinuity at x equals 9 by calculating the limits from the left and the right. Okay, so how do we know that it has jump discontinuity? Well, that means that the function value would be different than the limits, that the y value. So let's look at f of 9. Okay, so piecewise function. We're going to use this function if our values are less than 9. If our value equals 9, we're going to use this function. So that's the function value right there, 14. And if our values of x are greater than 9, we're going to use this function. Okay? All right. So just kind of looking at this graph. So my function value is at 9. There's 14. So right there. Okay? That's the function value, the point. That's where that point is. Okay? So now we're going to look at the limit as x approaches 9 from the left, okay, of f of x. Sorry about that noise. All right, so if we're going from the left, then that's numbers less than 9, so we're going to use x squared plus 5x plus 5. Okay. So that's what we're going to do. So we're going to plug in 9 here. Okay. So we're going to do 9 squared plus 5 times 9 plus 5. Okay, so that's 81 plus 45 plus 5. So we end up with 131. Obviously not the same value, so there's a big jump, okay? Now, remember what this is. This is a parabola. So I'm going to come up here to 131, okay? So at 131, that's the limit, and this is a parabola, so it looks something like that, okay? So the parabola has a limit as we approach 9 from the left at 131. So there's definitely a jump discontinuity there. Okay. Now let's look at the limit on the right. So the limit as x approaches 9 from the right-hand side means we're going to use this function. So now we're going to do the limit as x approaches 9 from the right of negative 4x plus 4. We're going to plug 9 there. So we've got negative 4 times 9 plus 4. So negative 36 plus 4 is a negative 32. Okay. So now we're at 9, negative 32 down here. And what kind of equation is this? This is a line. Slope is negative, so the line goes down. So this would look like that, right? So there's definitely jump discontinuity on both sides of this. So that's that piecewise function right there is what it looks like. Okay, so right at 9, the function value is 14. So there definitely is. And it just said to show. So, I mean, we showed it by, looking at these function values and the limit values. Okay, so definitely not continuous. That's what we would call jump. Right? Look at the graph changed. So that's a jump discontinuity. Okay. Now we have some theorems to go over and a couple more problems, and we will be done with this section. So this theorem is kind of the same as the limit theorems, where it's just kind of common sense. It says that if f and g are both functions and they're both continuous at this value a for some number a, and then c is a constant in any problem, but more importantly, we're looking at the limit or the function value being continuous at a, then the following are also continuous at a. So again, if f and g are both continuous at a, then all of the following are also continuous at a. So if you have two functions that are continuous at a and you add them together at a, that will also be continuous. If you have two functions continuous at a and you subtract them at a, that value will also be continuous. Same thing for multiplication, same thing for division, as long as you're not dividing by 0. And then this is the constant part. If you multiply by some constant, you're still going to be continuous. Again, all of those are continuous when you're talking about a specific value that you already know is continuous on both of those functions. Okay? All right, these two theorems I wish was earlier when we were talking about, all those domains. So we've already kind of talked about this, but these are theorems. Polynomial functions are continuous everywhere, and rational functions are continuous everywhere it's defined, which means, remember, where is it? It's defined everywhere except what makes the denominator equal to 0. Okay, so that's the piece of rational functions you got to remember. What makes the denominator equal to 0? Those are the places where the function is not defined. Okay, all right. Next page is where we're going to end today, which is the intermediate value theorem. Now, this theorem is hugely important when we're looking for zeros. That's the whole point of this function, this theorem. This picture, I don't think, does it justice, so I'm going to change it up a little bit after we go over this and explain why. So what the intermediate value theorem is asking us to do is look at function values and see how they change, okay? And then being able to know that if the function values are not equal, then we can always find a point in the middle that's somewhere between the two function values. So it's kind of a common sense theorem, but there's a lot of information here. So I just want to make this clear to you guys. So the theorem says that if f is a function that is continuous on a closed interval from a to b, so we're only looking from here to here, okay? So from a to b, closed interval. So if we have a closed interval and n is a number between f of a and f of b, so it's telling you, now remember, these are the y values, right? This is the y value. Okay, and then these are the x values up here, right? All right, so f of a is the y value, f of b. Okay, so we have these two values cannot be equal. So basically we can't have them right here. Okay, we can't have a horizontal line. That would not work. So all this is starting you off saying is that the function has to move up or down. Could come down, doesn't have to necessarily go up, but the y values have to be different. Okay, that's what that says. So if the y values are different, then obviously somewhere in between those y values, there's another y value that's between those two. And that's just common sense. There's no other way that could be. It has to be between those two guys. All right, so what this intermediate value says is that if we can find this value, then we can find its corresponding x value, and they're calling that c, and c has to be between a and b. Well, again, if you look at that picture, that pretty much makes sense. If you have these 2 points and you find a middle point, well, that middle point's the y is gonna be between the 2 y values, and the x answer is gonna be between those 2 x's, okay? So that's what that says. But the whole reason that this is for us and in algebra, it was to help us find roots. So in this day and age, we don't use this intermediate value theorem very much because of the fact that we have a calculator and we can find roots easy. Remember, the root is where it crosses the x-axis. Okay, so I want you to think about, I'm going to do this same graph, but I'm going to put it on the xy axis. Okay, so I'm going to draw it like this. Try to make it look the same. Okay, so there's that same graph, but this time I'm putting it on not where it kind of was here. I'm putting part of it below the x-axis and above. So here's why this is real important. So hopefully this will make sense to you. So this time I'm going to pick a that's down here. Okay, let's say that's my a value. And over here I'm going to pick b. So there's that interval from a to b. So here's f of a, the y value, and here's f of b. Okay? Now, I'm just going to make up a number. So let's say this is -10, and let's say this is 30. Okay? All right. Well, if f of a equals -10 and f of b equals 30, then I can find a point between I can find lots of points, but most specific, I can find this point right here, and that is a 0, right? That's the root of this problem, and I know that there's a root. Why do I know there's a root there? Because if f of a was a negative number and f of b was a positive number, then I know that 0 is between those two, right? So there's always going to be a 0 between f of a and f of b as long as the signs change. One's positive, one's negative. That's why this is really important. Okay, just to find a number in between, that's not very exciting. But when that number you're looking for is a root, that's the solution, then yes, that's important. So in number 14, it says show that this quadratic equation has a root on the interval between 1 and 3. Okay, well, yeah, I could graph that. That would be real easy now, but let's say I didn't have a calculator. Well, if I looked at where f of 1 was and where f of 3 was, and I can show that those signs change, that's all I need to do, okay? So let's look at f of 1. If I find f of 1, 1 squared minus 1 minus 2, okay, 1 squared is 1, 1 minus 1 is 0, minus 2, so we get -2. So again, on this graph, I've got the point 1, -2. And remember, this is a parabola, right? I know what the shape of this is. Now, if I find f of 3, 3 squared minus 3 minus 2. 3 squared is 9. 9 minus 3 is 6. 6 minus 2 is 4. So at 3, I'm at 4. Okay? So, by the intermediate value theorem, if f of 1 is a negative number and f of 3 is a positive number, there has to be a number between a y value between a -2 and a +4 where it's 0. That has to be true, okay? So if I look at this parabola, kind of goes like that, okay? So I can see very clearly that I'm going to find a root. So the neat thing about this theorem is when I know that signs change for y values, I know I can find a 0, okay? So that's what that is asking you to do. And so this is what, that's showing it right there. You showed that the values changed. Okay, so we could say by the intermediate value theorem, just abbreviating, there exists a number c, okay, between 1 and 3, where f of c equals 0. I know that there's some number c right here. There's a c. I don't know what it is. It's not necessarily 2. But there's a c somewhere between a and b. Right? Here's a and here's b. I know there's a c value in there that equals 0. Okay? So that's what you're trying to show by the sign changes up here. Now, if they both were positive, then I can't find that. Remember, 0 is between positive numbers and negative numbers. Okay? So I know I spent a little time on that, but you know, the intermediate value theorem is real important in calculus. And again, the way that it's written doesn't really do it justice because we're looking for zeros. We're looking for solutions, and those are important. Okay? All right, last problem, which I'm pretty sure this is a web work problem, and there's no work to be done, so you just have to kind of read it carefully. It says, let f be a continuous function such that f of 1 is less than 0 is less than f of 9. Then, by the intermediate value theorem, implies that f of x equals 0 on the interval between a and b. Give the values of a and b. All right, well, let's remember the formula. Okay, remember that a and b, and these are the x values, right? Any interval where you're given this is x. So they want to know the x values of the interval. Well, remember the formula, the interval a and b, those are your x values, and then f of a and f of b are the y values. So these are your x values, the numbers that are in here. Okay? Remember your function notation, right? If you just did it right here. If x equals 1, that's the x value, then f of 1 is the y value. So this is the x value that's in here. So they gave you those. So 1 is the lower end of that, and 9 is the upper end. So a has to be 1, and b has to be 9. They were this is just, do you understand the notation? Okay? So that's real important that you know f of 1 is the y value, which means x is 1. F of 9 is the y value when x is 9. So those are already your x's right here. That's the x1 and the y1. Oop, x1, x2. Sorry about that. Got ahead of myself. x1, x2. So those are your x values. Okay. All right. So that does it for this section. So you got your notes check quiz to take. You've got web work to work on. Please get help if you are struggling already. Don't feel bad about it. Just get the help so that you can do well in the class, okay? All right, you guys work hard and let me know if you have any questions.